What if I told you that every number you've ever seen has a secret code, a hidden identity that's totally unique to it? Well, today, we're going to crack that code. So, is that really true? Do numbers have a secret code? The answer is a huge, resounding yes. And this isn't just some quirky fact. It's one of the most powerful ideas in all of mathematics. It reveals a beautiful, hidden order to the universe of numbers. To get our heads around this, let's think about it this way. We're talking about the DNA of numbers. You know how every living thing is built from a unique genetic sequence? Well, it turns out numbers work in a very similar way. And the fundamental building blocks for that DNA? They're the prime numbers. Numbers like 2, 3, 5, 7, 11, the ones you can't divide by anything other than 1 and themselves. You can think of them as the indivisible atoms of math. You just can't break them down any further. Everything else is built from them. This is a perfect example. Take the number 30. You could say, oh, that's 5 times 6. And you'd be right. But 6 isn't a prime atom. You can break it down again into 3 times 2. So the ultimate fundamental DNA of 30 is the set 2, 3, 5. And no matter which way you slice and dice it, you will always end up with those 3 primes. And that right there is the core idea. Every single whole number bigger than 1 is either one of those prime atoms itself, or it's a molecule, a composite number, that's built by multiplying those prime atoms together. It's a rule with absolutely no exceptions. Now, this isn't just some neat party trick. Nope. This concept is so important, so central to how numbers work, that it gets a very grand name. It's considered a fundamental law of mathematics. And here it is, the Fundamental Theorem of Arithmetic. Now, that sounds a little formal, right? But it's actually saying 2 very simple, very powerful things. First, that you can break any composite number down into primes. But second, and this is the part that changes everything, that breakdown, that prime DNA, is completely and totally unique. So let's really zero in on that. Part 1, existence, is cool. It tells us we can always find the building blocks. But part 2, uniqueness. That's the real superpower here. It means the number 30 will always be made of 1, 2, 1, 3, and 1, 5. Period. It's a universal fingerprint that can't be faked. Let's put this to the test with a big, beefy number, 32,760. We can start breaking it down any way we want. Maybe you see the 0 at the end and think, okay, let's pull out a 10. Great. Then you might notice 3276 is divisible by 4. You just keep going, breaking down every piece until you're left with only prime atoms. And the magic is, no matter what path you take, you will always end up with the exact same collection of primes. 3 2s, 2 3s, 1 5, 1 7, and 1 13. That's its unique DNA sequence. Now, this idea had been floating around since ancient Greece, but the guy who really nailed it down with a proper, rock-solid proof was this guy right here, Carl Friedrich Gauss, the prince of mathematicians, which just goes to show how deep and important this seemingly simple idea really is. Okay, so we have this incredibly powerful tool, this law that guarantees every number has a unique prime code. What good is it? Well, how about we use it to solve one of math's most famous and ancient mysteries? And the mystery is this. How can we be absolutely 100% certain that the square root of 2 is irrational? I mean, we know it's a number. It's about 1.414, but what does irrational really mean, and how on earth do you prove something like that? An irrational number is just a fancy term for a number that you can't write as a nice, simple fraction of 2 whole numbers. Its decimal is a total wild card. It just goes on and on and on forever without ever repeating a pattern. But, proving that something can't be done is a really tricky business. And this is where our fundamental theorem becomes the master key. We are going to use the ironclad logic of a unique prime DNA to crack this case wide open. And we're going to do it with a really clever technique. It's a method called proof by contradiction. It's kind of like playing detective. First, you assume the very thing you want to disprove is actually true. Then, you follow the logical trail from that assumption. Eventually, that trail leads you to a dead end, a complete logical impossibility. And if you hit that wall, it means your initial assumption had to be wrong all along. All right, let's do it. Step 1. We're going to assume the exact opposite of what we want to prove. Let's just pretend for a minute that the square root of 2 is rational. That means we can write it as a fraction, a over b. And let's say this fraction is as simple as it can possibly be, that a and b have no common factors. Okay, next up, a little algebra. Don't worry, this is the easy part. We just square both sides of the equation to get rid of that pesky square root. Then we multiply both sides by b squared, and that leaves us with this beautiful, clean equation. A squared equals 2 times b squared. Now, let's be detectives. What is this equation telling us? Well, look at the right side. It's 2 times something. That means a squared must be an even number. And here's a fun fact. If a number squared is even, the number itself has to be even too. So we've just proved that a is an even number, which means it has a 2 in its prime DNA. Let's follow this clue. Since we know a is even, we can write it as 2 times some other number. Let's call it c. Now, watch what happens when we substitute 2c back into our equation for a and simplify everything. We end up with a new equation, b squared equals 2c squared. And this right here is the final piece of the puzzle. Doesn't that equation look familiar? It's telling us the exact same thing, but this time about b. It means b squared is even, and therefore b itself must also be an even number. So b also has a 2 in its prime DNA. And there it is, the contradiction, the gotcha moment. Remember what we said at the very beginning? Our most important condition was that the fraction a over b was fully simplified, that a and b had no common factors. But we just logically proved that a is even and b is even, which means they do have a common factor, the number 2. Our one starting assumption, that the square root of 2 is rational, has led us down a path to a conclusion that is logically impossible. It completely breaks its own rules. The only way out of this paradox is to admit that our starting assumption was wrong from the get-go. The square root of 2 simply cannot be written as a fraction. It must be irrational. Case closed. So we cracked the code of numbers and used it to solve an ancient mystery. Pretty cool, right? But why does any of this really matter? What's the big takeaway here? It all comes down to the power of uniqueness. This theorem pulls back the curtain and shows us a deep, beautiful, and hidden order that governs every single number. It's the cornerstone of a whole field of math. But more than that, it gives us the logical key to prove things that otherwise seem totally unprovable. It shows that a simple, elegant rule can have the most profound consequences. And that leaves us with a pretty incredible thought, doesn't it? If a rule this simple can have such deep implications, it makes you wonder, what other fundamental rules about our universe are just sitting there, hiding in plain sight, waiting to be discovered?